Tonight, well, we're going to be talking about dye line detection in plastic bottle manufacturing. Just a simple recap of the last time I did a presentation, then what exactly are dye lines, what caused them, how I plan to detect them, and how I intend to actually implement it. So just as a quick recap, I'm not going to explain this whole thing. Just you're following the green fluid, that's the melted plastic. And basically, if you look at 9 and 10, that's where the plastic comes out in a kind of hollow tube, and you'll see that just now. So basically, one, which is the plunger, just pushes all the plastic melt forward and squeezes it through 9 and 10, and then you end up with a plastic tube that looks like this. And then air fills, well, a mold clamps around that, and then air is filled in from the top, and it ends up taking the shape of the mold that it's in, and that's how you actually get a plastic bottle. Um, so dye lines specifically are surface striations or stretch marks. They aren't actually stretch marks because the material isn't stretching, but it looks like stretch marks along the length of a plastic bottle, right? Common causes for it would be foreign matter, so dust or metal from regrind. Regrind is basically when you recycle a bottle inside the production process, like you take waste and then you dump it into the regrind, the metal from the blades could chip off and things like that and actually be present in the regrind. And then the regrind is reintroduced into the process with fresh resin, fresh plastic resin. So that way you minimize the actual wastage in your production. But yeah, so foreign matter, accumulated plastic due to uneven surface finish. I'll show you a picture of that just now. And colorant or additives melting faster than resin. So due to the dynamic nature of plastic production, sometimes you won't get resins from the same manufacturer all the time. And similarly, you won't get colorant or additives from the same manufacturer all the time. And the slight differences between trying to match resins and colorants and additives, sometimes you'll have to create a different formulation and test it and make sure that everything melts at the same rate so that something doesn't melt faster and then burn, and then your resin isn't even fully finished melting yet. So everything has to be basically a fluid before it gets pushed out. And the dye lines could actually represent mechanical failure because if you think about a cross section of a bottle, dye lines would be just the bumps on either the surface or the inside of that wall, of the bottle wall. And that would represent uneven plastic distribution or uneven material distribution. So if the bottle falls, the place with the least amount of plastic on the bottle wall would experience the most stress and it could burst. And well, this has happened in the past. So the mandrel and the dye is this part right here. And this is where the plastic gets pushed through. And right here is where you could have foreign material or that plastic buildup that'll actually cause those dye lines to appear. And this is a really a really bad case of it, where we had a lot of material being built up on a mandrel, and this uneven machine surface caused some problems too. So, and this I think is not cheap to replace. So what what we would do is we would machine it internally and try to get rid of all those ridges that you see in there. Now, if you actually touch that, that's really smooth, but to the plastic or in the process, really going to cause a lot of problems. So how we plan to detect the dye lines is by investigating 3 methods. One of them is to get uniform images around the bottle and then compare those images with images of good product. And One method is image histogram comparison. So basically, just convert the images to hue saturation value format, calculate the HS histograms, and for the good product and for the product that's on the test, and then make a comparison using four metrics: correlation, chi-square, intersection, and I'm sorry if I butcher this pronunciation, um, but uh, but a carrier metric, and then make a decision based on those metrics whether dye lines are present or not. This is taken from the OpenCV documentation. So they just have a hand here. This figure 8 is the base image, and 9 and 10 are the test images. And with correlation and intersection, the higher the metric, the more accurate the match. So if you look at the base comparison here, it is a straight one, intersection is 24. And with chi-square and the other one, it's the lower the value, the higher the similarity of the image. Or, yeah. So you see it's a flat zero for the base image. Base half is they just take half of the base image and made a test with it. Base test one is a comparison between base image and test one image. And well, base test two is base and test two. Now, yeah, so these histograms would give us an idea of how closely the surface of a bottle at a particular point, well, a bottle on a test at a particular point would match an image of good product for that same position on the bottle. Another method we're going to look at is the mean squared error. Just get the image difference by subtracting pixel intensities for each corresponding pixel. A value of 0 indicates perfect similarity, and a value greater than 1 implies less similarity. And the value will continue to grow as the difference between the pixels increases. But large distances or large values really between pixel intensities don't really mean that the content of the images are dramatically different. And that's where method 3 will come in, which is the structural similarity index. And this one is based around the idea that pixels have strong interdependencies when they are like close together. So one pixel by itself doesn't mean much, but you can kind of get some context as to an image based on the surrounding pixels. And this one generates a result between 1 and -1, where 1 indicates similarity. And all these methods have already been implemented in OpenCV and Scikit. So to do the actual math behind them is not really a concern right now, unless we would have to optimize it. But they would still have to be performant because the time between the longest time between a bottle is 3.5 seconds. And we also have to consider the platform that this might be running on, which could be a Jetson, in which case we have a lot of processing power, or it could be an embedded system like that new Arduino that launched with deep learning capabilities. I can't remember the name of it. I think it's TinyML, but it could be something like that as well. So this is a comparison between the mean squared error and the SSIM. So on the left, you just have this image of Jurassic Park, and on the right, you have the image of Jurassic Park with the Jurassic Park logo overlaid on it. And the MSE for this is 1076 and the SSIM is 0.69. I forgot to include the photo before this, but basically the photo for the okay, I can't remember the original metric, sorry, but the SSIM basically gave a more accurate indication that there was something that was different about the picture on the right as opposed to the MSC. And that was just an an indication that the SSIM was better at detecting contextually different images, even though the the pixel values for these two images at each point on the image were relatively the same. So in the coming weeks, we're gonna look at these three methods and test them. Well, the image histogram is one method, but it also has four metrics, the mean square error and the SSIM, and then record the time taken for each of those comparisons to run. Now, I did select die lines to do the defect detection on because that's what we were having a lot of problem with. But then we solved that problem. So I could still apply it to something in film, but just a different for plastic film manufacturing. But it would just, the implementation of it would be different, but the computer vision behind it would still be the same. So that's it for my presentation. Um, are there any questions?
Simeon, interesting stuff. So now that they solved the problem with the bottles, did they adjust their sampling rate as to how often they sample to check for problems, or?
No, it would be the same. It would be the same rate because even though it had problems um, with the bottle, the current sampling rate was still enough to get them and flag them. The only thing is that it's a manual review process that takes very long, and they would. Well, when I say very long, I mean like a couple hours, and they would have to do it by batch, and that's not a ideal situation.
Okay, so even if they solve the problem you were looking at initially, this project should help them as well still, right? Because if you could show that the you could do as good a job as the humans, then you'll be saving some money,
Yeah,
right?
some well, money and manpower, and
Right.
it's not that it could only be applied to one part. We have I think it's seven blow molding machines, and then well one four extrusion machines. So basically, it has 13, 11 machines that could produce product with die lines. So if this system is implemented across those 11 machines, then that would be a really big help.
Okay. And one last thing, will you be able to do this fast enough to check each bottle, as opposed to in their case they take samples, right? So they don't really check everything. Would you be able
Well,
to do this quick enough?
so the reason they don't check everything is because of the labor involved. Once they don't check everything, they don't inspect every bottle because the problems that would occur for one, the nature of the process is that it would actually occur for the entire batch.
Okay.
So they just have to sample about 10 bottles per batch. The batch size would vary, and
Okay. No, no. All right. Yeah. So potentially you could save quite a bit of money by
yeah.
deploying this. Yeah. All right. Thanks.